So networking technologies is the next topic. Relatively long set of slides, relatively long topic. The networking technology will talk about TCP IP properties and characteristics. TCP, Transmission Control Protocol, IP, Internet Protocol. TCP is going to be the thing that controls how we connect, where we connect. IP is going to be the addressing. And then the TCP IP, Internet connection, ports and protocols. Ports are a big deal because services are things like a web server, an FTP server, file transfer protocol server, run at specific port addresses along with the IP address. So protocols and ports are going to be related to each other. And then at the end, we'll talk about some networking tools, physical networking tools, as well as some virtual networking tools. So when this starts out, we talk about layers of network communication. Two devices communicate. They must use the same protocols. And protocol is just simply a language. The only protocol set that we use today is TCP IP. There have been others in the past. NetWare used to have their own. Microsoft, NetBIOS used it, but and it's still available in Microsoft. But TCP IP is the protocol that we're going to use. It's the protocol of the internet. It's the way the internet connects together. Communications happens in layers. Applications pass a request to the operating system, which passes the request to the network card and then onto the network. When you do Network Plus, you'll go through a thing that says, and I've got a note here, says this is part of the exam and the SOHO as well. So this is part of the exam. And I'll be watching for notes if anything particular comes up. This individual, I'm sure, will say, oh yeah, pay attention to that one. But happens in layers. Again, when you get to Network Plus, you're going to study a model called the OSI, the Open Systems Interconnect model. Also one called the TCP model. They do the same thing, it's just how much each of them has. But that's what we're talking about here when it passes it down from layer to layer. So we start out with we start out with our web browser. Our web browser then sends information to the computer through the memory, the RAM, and the cache to the processor, processes it. The processor then eventually sends it to the NIC. The NIC sends it over the network to the destination address, the destination IP address, where it's going to go up that magic stack. Goes through the NIC, goes into the memory, into the cache, into the CPU, and then gets delivered to web browser, gets delivered to the web server portion of it, the thing that's going to provide us with web pages. So we connect to the web pages on the web server, then it gets sent back via a reverse path. And that's what we're talking about when we talk about between the computers happens in layers. The level one here we're going to talk about be a hardware layer. The root level of communication, wireless or network cables, phone lines, TV cable lines. In the hardware portion, we connect the NICs together. Obviously, we talked about switches and hubs and all of those different things, and we had bridges, different ways to physically connect these things together. We'll have one here in a second. A NIC has an address that's known as the physical address or the MAC address. So it has a physical address, and it's going to be unique. And it's sometimes called a BIA, a burned-in address, because it's burned in by the manufacturer when the device is created. So this is going to be a unique address, the MAC address, unique address, burned-in address at the manufacturer. known as the hardware address, physical address, adapter address, or Ethernet address. So it's got a lot of different names, but it's this 48-bit, it's a 48-bit hex number, hexadecimal address. The first half is the manufacturer. You can look those up on the internet. So we're going to have 24 bits is going to be the manufacturer, whoever makes it. And 24 bits is going to be what I call the serial number, or the uniqueness of it. So the MAC address is used to locate a computer on a local network. We're going to talk about IP addresses. IP addresses are not permanent. They change. So the IP address actually finds the network. And it is kind of like if you are going to visit somebody that lives in an apartment. The IP address would be maybe the address of the apartment building. The MAC address uniquely finds the individual would be the apartment number, the floor, and the room number that goes with the apartment itself. So the MAC address, the hardware address, unique address, 48-bit address, all of the networking devices, NICs, all have those addresses. This is a NIC here, a blow up. The MAC address here, you can see on it, was it 6805 CA08 A056. So that's going to be the unique address. This is the only networking device that should have that entire address, that complete address. This over here is going to be the serial number, the device number, the part number of the device itself. But the MAC address helps us to find the computer. The NIC card itself, again, shows the physical address, the network connection port, and then status lights. These things, some of them have status lights, some of them don't have status lights. They'll tell you, and if this one turned around, I think it's a 100 meg and a 10 meg would tell you how it's connected. The lights flash when traffic actually gets sent through the wires itself, sent across the network. But a NIC, an RJ45 connector, what a NIC looks like here. The network connection port, one or more ports that are configured to connect specific types of network cables. And the only ones that we're really going to use today are going to be twisted pair, RJ45s, or fiber optics. Fiber to the computers has not been very profitable, I guess, because fiber costs a whole lot more to make than does copper wire. A fiber end costs, I don't know, maybe $5. An RJ45 costs, maybe 50 cents. A crimper to make a wired cable, an RJ45, costs maybe a good one, maybe $85. A fiber microscope to inspect your connection costs $8,000 to $10,000. So we're going to have to our devices are predominantly going to be wired connection, RJ45. We'll talk about the cats here in a second. Physical address, we've talked about it. Globally unique physical address assigned by the card manufacturer, called the MAC address, and we had that list of other things that were there. The LEDs, status indicators on the back. The link light says when it comes on, a link light is a pretty big deal, and you have link lights on switches and hubs also. That just says that the wire's connected to it, that we got the wire connected to it. Activity light says that there is activity, and then the speed light there, which speed are we going at? And on a switch, you got two of these things, and one of them is 10 meg. If it's a 1000 gig, maybe one light would be 100 meg, and two lights would be 1000 meg of gigabit connection. This one kind of gets thrown in as Ethernet, CSMA CD. What this means is, in Ethernet, what is Ethernet? Ethernet is basically a piece of coax. It has T connectors, that has computers connected to it. We looked at T connectors. It has a resistor at the end to absorb, terminator resistor at the end to absorb excess signal. So it's called contention-based CSMACD. Carrier sense, it's going to have a carrier signal because in order to be able to send data across anything, we have to have a carrier. And a carrier is just a constant frequency that we're going to make changes to. Multiple access, we have a whole bunch of computers here connected to the same piece of wire. This is kind of like getting on a highway. That everybody's trying to get on a busy street at quitting time. We want to go home. We want to get on the street going out of the factory or wherever we're working, wherever we are. Carrier sense multiple access collision detection. What that means is that when one of these devices wants to send something, it listens to the wire, to the network, to see if anybody else is talking. If they're not, then it's going to send its data. It's going to put its data on the wire, and it will fill the entire wire. So carrier sense multiple access, and after it puts it out here, it's going to listen to see if there's a collision. If there is a collision, then we're going to get what's called a jam signal, which says, oh, been a problem, we had a collision. So the jam signal says, start over. Does a random back off. If we did a fixed back off for both of the devices that sent things to cause the collision. Let's say that maybe this guy sent one too. They sent them at the same time because when they listened, nobody was sending anything. It was good. But when they sent, they both sent at the same time. A collision, jam signal, random back off. RNDOM. Random back off and then start all over. Listen, nobody talking, send it. Each of them's going to get a different amount of time to wait. So CSMACD bus, and the bus is because they're all connected to the same piece of wire. And this is the original Ethernet. This is what a true Ethernet is, and it's called a contention-based sense system. Contention-based, also called a probabilistic system. You're probably going to get on the network, but there's no guarantee. We talked about token ring, I think early on. Token ring is a deterministic, you're guaranteed access, you just don't know for how long. The other layer of communication is the operating system. Manages communication between itself and another computer using TCP and IP. TCP, Transmission Control Protocol, IP, Internet Protocol, the addressing itself. So from computer to computer, and this shows that on a LAN, it's going to be the MAC address. We also, and we do. So we have this guy comes in, it's an IP address, maybe 192.168.1.6 comes in, and it's looking for the 192.168.1.6 network. We have a protocol called ARP, Address Resolution Protocol, that will translate this IP address to a MAC address. FF0123, whatever. I'm not going to write the whole thing out, but it'll translate it to a MAC address. And the MAC address is then going to find the individual computer. It's unique. IP addresses change. They don't necessarily change, but IP addresses to change. They are temporary addresses. Does everybody just want to poke my eyes out, or does it make some sense? Nobody's screamed yet. I get it makes sense. Okay. Some sense. We're getting there. Some sense. Two different addresses. The one that gets you, and what an IP address does, this says communication through the internet, communication. Routers send IP addresses across the internet. So we would put our IP address out on the internet, our destination IP address, and it would get over here into this network. But how do I find that IP address? The only way to find that IP address is with the MAC address, and that's what this communication is by MAC address is trying to show here, that they're on the same network. The router is going to find the network that it's on. The ARP protocol is going to find the specific computer that's associated with that IP address. 32-bit IP address, 32-bit or 128-bit. 32 bits, 32-bit, and I'm gonna wait. Let's just say that that's that. I got some examples of what that means here in a few minutes. But a 32-bit, 32-bit, 32 ones and zeros, 8 bits per grouping. Or 128-bit, 32 bits an IPv4 address, 128 bits going to be an IPv6 address, which has got a tremendous number of addresses in it. We're going to look at the numbers of addresses in each of these here in just a couple of minutes. Used to find computers on networks and subnetworks, including the internet. It actually is used to find networks. The whole protocol stack, the network communications, gets it into, so they all have their own IP address, but when you send something, it is only sent via MAC address, right? Yeah, kind of, sort of. How's that? So we all do have, let me try that again. We all have an IP address, right? And we all have a MAC address. So what I have, my address is 192.168.1.7, and I'm trying to get to over here 192.168.7.8. The routers will use the IP address to get it over here to this network. So we've got the internet here. So it's going to go across the routers to get to this network. When it gets here, our ARP protocol will use this IP address, the destination IP address, to find the MAC address. Does that make any sense? Okay, let me try this, because we can look at it. If I make that stuff go away. This is the command prompt on the computer that I'm on. If I do ARP, gotta spell ARP right though. ARP-A tells me to look at all of the associations. 192.168.253.254. Here is its physical address. Dynamic means that the computer found it, and we have a bunch of statics in here. 224, and these are addresses that you really shouldn't know about yet. Multicast addresses, broadcast address down here. These are all. This is the one. These are all virtual MAC addresses up here. The 192.168, the 200, and both of those are. This is the one that actually I'm using on the physical machine, the 192.168.1 network. Its address is 27. The default gateway MAC address, so I can send it to that MAC address. This is one of the other machines, and another machine, another device that's on here, and then I have a broadcast. Broadcast sends it to everybody, and broadcasts are all 255s here, or 255 at the end. We're going to talk about addressing in a little bit. FFs our broadcast would say go to everybody. So ARP to command prompt. And I can't show it, if you go to the type or search command, it's a command line, and type CMD, you will get this box here, which is a command line. It's called, not GUI, command line. We can give Windows commands through this thing, but we typically are going to use the GUI in order to do that. But the command prompt can do different things. We're going to look at, if we wanted to look at the IP addressing information on it, and I would use the IP config. Show me the IP configuration. Have IP addresses, the same one we used. Have a subnet mask default gateway. These are things that we're going to talk about. What are they like? So there are some things you can get out of the command prompt, the command line in Windows. DOS, that's all DOS had. For anybody that may have had DOS, it was all command line. But when we went to the GUI, the graphical user interface, Windows left in the command line so that we could give it specific commands without having to go through the GUI. It's a little bit quicker when we do these things. Layers, a level 3 application communicates with server applications, a web browser. We talked about that. Email server. Port number, port address uniquely identifies a computer application. We're going to get a list of those in a few minutes, but one that you use every day, port 80 or port 443 for secure, is for a web server, a web server. So when we go to a web address, http www.leaderquest.net, we go to an address. The internet, the routers take control of the IP address, route it across the internet. When we get to the network that server's on, we find the MAC address as well as the port, and if we did HTTP, it's going to look for port 80. It latches on to that particular one. This is layers of communication. This is a little bit about ports. Each service has a unique port number, and that's part of what we're talking about. That, yep, things like that. There are certain ones that you need to know are going to be on the that you will be expected to know on the test, and after you do them for a while, they're just going to be the few you say, okay, yeah, I know those. But this guy comes in and says this is for 138.60.30.5 colon 80. The colon says that it's going to be for port 80. And here we have the email server is going to be on port 25. Well, that's not port 80. Port 80 over here, the web server, I'll take port 80. I'm port 80, I'll take it. So it takes that one. And when we have an IP address bonus here, an IP address and a port together, that's called a socket. So that we're going to come back to the port numbers in a minute. Now we're going to jump to some media. Little bit easier to comprehend and look at, I think, but this is what twisted pair looks like. These are the things that connect to the RJ45, and as you can see here, it's got 1, 2, 3, 4 wire sets, but there are 2 wires twisted together in each of these, so we have a total of 8 wires. The twists help to reduce the amount of noise that that will go through these things. The insulated jacket there is just a plastic sort of an insulation, but we use these things. We until we get into the 5E and 6 areas, we only use 4 of these wires. When you untwist them, they're going to be an orange and white, an orange with a white stripe, a solid orange, green and a white, a blue and a white, and a brown and a white. When we look at those things, and those are going to be used in the standards here in a few minutes. Unshielded twisted pair, 4 pairs of twisted 26 gauge. Twists provide protection from crosstalk. What crosstalk is if we have, I'm an electrical engineer, so I can hopefully do this. If we have a noise signal comes in here on one of these wires, it's going to be induced into the other wire. When we twist the wires, we physically shift them a little bit so that when we get this one and we get these together like this, they're going to cancel each other. So we get some noise cancellation by using the twists. The most common types now are Cat 5e and Cat 6. Table 111, which you want to have, this is from another presentation for the details. We're going to have some details of these things. Shielded twisted pair has a metal braid around it, so it actually has a shield, and it's going to be a little bit more resistant to noise. The next thing that is in here, and these unfortunately, I think I got some of my slides in odd orders, but fiber optical cable types, and I've got a picture a little bit later on that gives you a better idea of what a fiber cable looks like. But this says it's a thin core, signals up to 60 kilometers. That's a long way. It's a whole lot farther than the 100 meters that we can get with our copper wire. A laser diode as the light source. Laser being the key word here. We're going to have a high-powered light source, and this is single mode, and a couple of things that one of the objective types was single mode and multi-mode. So single mode, signals up to 60 kilometers, laser, cable, TV, phone. Cable TV uses fiber up to a point, and then they go with copper. Long range distribution, they're typically going to use that. Telephone systems are going to use fiber to send the signal. It's going to be single mode fiber. Single mode fiber has a single signal on it. Multi-mode, it's a thicker core. It can go up to 10 kilometers, which is a long way. It uses LED as a light source, used for the local metropolitan area network, LAN, MAN, local area network. For some things, if you're going between floors of a building, sometimes the fiber will go there. And I think these are the three connectors that they talked about. The LC connector here, and you notice there are two wires. One is for the transmit and one's for the receive. In the twisted pair, that's what the pairs did. Some of the wires are for the transmit, some of them are for receive, because the NICs actually have a transceiver. A transmitter receiver is part of the hardware in it. So we have the LC here, the ST or the straight tip, and then the SC connectors, the shape of them. The ST, the straight tip, is probably the easiest one to figure out. UTP and STP, I told you I'd jump around too much. The fiber one's actually out of sequence. And we're going to have some other fiber ones here in a minute. But the categories of these, Cat 3, you're not going to see Cat 3 anymore. It could go up to 10 meg. It was one of the original standards. Unshielded twisted pair, obsolete, replaced with a 5E, actually 5 first, now 5E and Cat 5. Cat 5, 10 base T or 100 base T. What these numbers mean here is the 10 means it's 10 megabits per second. The base means it's baseband, a single frequency, and the T means it's twisted pair. 10 base T, 10 megabits per second, baseband, twisted pair. 100 megabits per second, baseband, twisted pair. And these can go up to 100 megabits per second. UTP 4 wire pairs. So in these we use 4 of the 8 wires. 5E, 10 base T, 100 base T, 1000 base T, gigabit. 1000 megabits per second, 1 gigabit per second, baseband, twisted pair. Cat 5 is available in UTP, STP, 4 wire pairs. Cat 6, the same things, handles higher frequencies than Cat 5 and 5E. It's going to be more reliable, actually. 6A, enhanced version. 7 is a new one, uses a 12 connector CG45, backwards compatible with the RJ45. But Cat 7 is new one. It is just coming into production, but it's going to, and this is a 10 gig connection, 10,000 megabits, 10 gigabits. Unshielded, shielded. You can see the foil. This could be a foil or it could be a braid around it. But and we can also, if we wanted extra shielding, we could have a foil around the pairs and then a foil around each of the pairs. Unshielded twisted pair just has the the shield. Maybe this just has the plastic cover on it. RJ45, RJ11. RJ11 is a telephone wire. It's going to be much smaller. It's got 4 wires total. The RJ45 Ethernet cable has 8 wires on it. RJ45 connector here, RJ11 connector here. RJ11 connectors, telephone lines you'd find in a modem. So in these 568A and 568B, we have the colors of the wires, the orange and white orange, green and white blue, blue and white green. And this is the this is the order that the wires would go in before you put them into the RJ45 connector. And then you would use a crimper to basically put little pins through the wire to have an electrical connection. And then you've got another piece that goes across the shield to hold it in place. If we were going to make a straight through cable, not part of the objectives, but a straight through cable, we would use the 568B at both ends. If we were going to make a crossover cable, we'd use the B at one end and the A at the other end. But this is the order, and I don't think that they'll expect you to know that. Network Plus will expect you to know the order that they go in, and this is what they look at. The pins, the copper here are actually little pins that penetrate the insulation. You don't strip the insulation off of these things. Little pins penetrate the insulation and make electrical contact. And then right here, which you probably can't really see, is a plastic piece that gets pushed down onto the case to hold the connector in place. Twisted, let's do this one. Actually, let's do a couple more and then we'll take a break. Probably tired of me already, but Cat 3, network type, telephone, Ethernet. This is the same thing. The frequency 16 meg, but you notice the frequencies change. As the frequencies increase, then we can put more data on it, because the frequency is the number of times the signal changes back and forth. If we have 16 million changes, we can't send as much information if we have 100 million changes. So Cat 5, fast Ethernet, 100 meg, 100 megahertz, 100 megabits per second, 100 megabits. Cat 5e, up to a gig, it still is 100 megahertz. Cat 6 goes to 250 megahertz, 10 megabits per second. 6A, or Cat 6 augmented, gigabit Ethernet, we can get 10 gig with it. It is a 500 megahertz signal. Cat 7, maximum speed 10 gigabits plus, and it's a 600 megahertz signal. More of what an RJ45 looks like, and then what the colors would look like in this thing. And if you look into it when you make it, you should be able to see the copper at the end of these things. But the 8 pins, 1, 2, 3, 4, 5, 6, 7, 8. When we go around these things, 4 pairs. The browns are here together. Notice that the oranges are separated. The blues are together in the middle, and then the greens are up here together. So how you would make one. The cable and Plenum cables, PVC casing is inexpensive, flexible. Problem with it, when it burns, it's poisonous. It produces a chlorine gas. Firefighters don't like it because they get gassed with it. Plenum cable has a jacketing that doesn't give off the poisonous gases or noxious gases when it's burned. So and actually it probably is the only one that you should use any place, but if you put it in a suspended ceiling or in a plenum, an air space of any kind, you need to use Plenum cable, and they'll be marked on the cable itself. It'll say Plenum on it, so it won't be any question about it. This one here doesn't show any markings, but you can see on the pink one here there are some markings on it, and it will have what kind it is, if it's what category it is, whether it's Plenum, and if it's on a reel, it'll have foot markings on it as how much of it you have used. So TIA, EIA, a commercial standard, A, legacy standard, B is the preferred cable type, C is the new standard, and that's I think where we need to go with those. What they do. They tell us what order the wires go in order to make twisted cable wiring. The next one is coax, and I will take a break after we do the coax, but in the coax we have a non-conductive insulated coating, a single copper connector in the middle, and then a braided shield around it. The braided shield keeps noise out of the system. It also acts as a ground. The reason it's coaxial is it is coaxial around the center conductor. The two different types of connectors that they talked about in the objectives are the F connector up here, the one with the threads on it, which would go on a splitter like this one over here. This one allows us to have one input and two outputs. A BNC connector here goes around goes on to a device that has pins on it. It's a quick disconnect, quick connect. It's still coax. It's got the pin in the middle, but the way it attaches is different. Different look at these things: an RGA connector, an F connector, and then the BNC connector. So, okay, we'll go from copper to fiber, and this is kind of what a multi-fiber cable would look like. It's got an outer jacket. The strengthening fibers there are usually going to be Kevlar. There's going to be a coating over each of the fibers itself, and then there's going to be a cladding, and inside the cladding is where the glass is going to be. Glass or plastic core. Glass, and these things are glass. If you've ever made one, you stuck one in your finger, you'll know they're glass. They do hurt. This is single core is what this one is labeled. Another picture of one, the strength member here on these things. Some of them have pieces of line or string in them that you can strip the outer coating off with. When you do these things, when you cut one, you don't really cut it. You score it and then break it, and then you have to polish the end to get it smooth. What you really do is basically glue the fiber into the fiber connector, which will then connect to our devices. This is another one that's got a lot more information probably than you want or would need, but 100 base FX fiber, length 400 meters, how far will they go? Fiber, we can't make the 100 meter, this is how far it goes deal. They're all a little bit different. Down here we get the single mode, 10 kilometers, the connector type, but fiber, ultra thin strands of glass, a variety of much longer distances than the 100 meters for UTP. Much less interference from the outside. There is no electromagnetic interference because it's light. Two types, the multi-mode and the single mode. Multi-mode, shorter distances, generally cheaper cabling, works fine with less expensive LEDs. The single mode, longer distances, more expensive, used with laser-based hardware. And this is kind of a picture blow up. This is a representation, obviously. We have the cable jacket, the strength member, Kevlar in here, a tight buffer, 900 microns, 900 millionth of an inch. The coating's 250 microns. The cladding is 125 microns. And then we finally get to the fiber core, which is in the middle. The way you check this stuff, the way we check this stuff, we had a flashlight that you'd shine through. You check it with a fiber microscope to see if it was cracked and if it had some issues. There were other things to check it, but just to check to see if it worked good, just a red light through it. This is the out of place one, which I moved down into another. This is just a picture of a number of different types of fiber. If you put it in, you need to use the right stuff. The one over here, the armored fiber, they had actually it was a fiber manufacturing company in Roanoke, lost all their internet connection because a rat chewed through their fiber. And they like this stuff. So if you're in a situation like that outside with squirrels or whatever else, you need to use the armored fiber in order to do that. Different types, and you can have here bundles. If we were going into a room, we would want to take a bundle in, and then we would run the different fibers to the different locations in the room itself. Types. These are illustrations of the single mode, small core, one mode of light to propagate one mode, think one frequency, one light color is an easy way to conceptualize that, I think. So that the number of light reflections is created as it travels through the core, lowers the attenuation and enables the signal to travel faster. Carries a single optical signal, small core, allows only a single beam of light to pass. A laser is usually used in it, and over here the multi-mode. As you can see, it looks like it's bouncing off of the walls of the fiber optic cable itself. We get some dispersion. Dispersion is the loss of signal, and the terms here, step index and grade index, are not really significant. These are images that are brought in so that we could see kind of what's going on here. Multi-mode is a larger core, supports multiple modes of lights to propagate, allows the number of light reflections created as it passes through the core to increase. More data can pass through, typically used for shorter distances. More data, more signals, more different signal types. The single mode, think single frequency, single signal goes on it. Multi-mode, we can have multiple signals on it, multiple light colors on it. This is just another fiber optic connections, without them being labeled, the connector types that you may see. And this is a table. I took the cable, made a table out of the book. The straight tip, the subscriber connector, the face connector, local connector, sub-multi SMA, sub-multi assembly, register connector, and then the uses over there on the right. Connect multimode fiber, box-shaped connectors to snap into the receptacle. So different ones, they all have the same purpose in life, which is to have light connectivity instead of electromagnetic connectivity. Another one, this is off of the out of Google Images, different descriptions of these things. The slides are available to you in the A+ share if you want to use it. Talk about wireless for a few seconds. We'll talk about radio waves and how to connect things wirelessly, but this is just an overview. The more wireless will be next week. The small office, home office configuration will be there. These are the ways that we can get there. And then in the laptop, the USB adapters here, USB to RJ45, a FireWire adapter, and then the other connections, RS-232 no modem. RS-232 is a serial port. Serial port's not really around a whole lot anymore. These are the wireless and these are just other ways to connect other network connections that may be available to you. TCP IP enables communication across different networks. It is the protocol, the language that we use to move information from one location to another. And we've talked about IP addressing a little bit and how it gets from point A to point B, but the network protocols, TCP, IP, and they usually go together. The dominant networking protocol in the world. I suspect that there are still a few people someplace that are using the old NetWare protocols, or some people are still using NetBIOS, which was a Windows protocol, and it's still available. Older versions of Windows need NetBIOS. The newer versions of Windows don't. What NetBIOS basically was a broadcast protocol that allowed you to see everything on your particular network segment. Been adopted, TCP, IP adopted by all manufacturers, network devices. NetBIOS, no network number in its structure, cannot be routed on the internet. It's a broadcast protocol useful only in a single broadcast domain. TCP is the only practical protocol to know. It's the protocol that the internet runs on, so it's the one that everybody's going to be using. Verifies that the data delivery process is successful. TCP does that. TCP is a protocol. Let me try another bad drawing here. Let me see where we are. Another bad drawing here. TCP, when it starts up, we're going to have two protocols, two what are called transport layer protocols. We're going to have TCP and UDP. TCP is going to be called a reliable connection-oriented reliable protocol. I'll have some better slides, but I'm going to try to do this. So connection-oriented means that before it starts sending data, it establishes a connection. It establishes a connection with a thing called a three-way handshake. Three-way handshake. And you'll learn a little bit more about this in Network Plus. But if I'm going from me to you, I'm going to send you first a packet, called a send packet, a synchronization packet, which basically says, I want to have a conversation. And it gives a number system where I'm going to start numbering my data that comes to you. You send back an acknowledgement, and then you acknowledge I want to have a conversation. And then you send me a synchronization packet. Say, but I'm going to use this numbering system to number my packets so that they don't get confused. I will then acknowledge your synchronization packet. After that, when I send data, I'm going to number it. It's not going to be 1. It's a big number. But I'm going to send a data packet 1, and you will send me back at ACK1. Acknowledge receipt of data packet 1, send 2. So I send you 2. And you say ACK1. But I just sent you 2. Well, I didn't get 2, so I'll tell you I got 1. When that comes back, it says, okay, I want to send 2 again. So then I will ACK2. Now I'm going to send 3. That's what makes it reliable. Because if something doesn't get there, it gets sent again until it's acknowledged. So reliability. Connection-oriented three-way handshake. We actually establish a connection. It's kind of like a phone call. I know you guys all text, but it's like a phone call where somebody calls you, hello, this is, hello, you say hello, the send packet, hello, this is, whoever, the other one, the send, the acknowledge, and then we start having a conversation. UDP is called connectionless and unreliable. It doesn't have any of these mechanisms. It doesn't acknowledge anything. It doesn't establish a connection before it starts. It just kind of starts having the conversation before the connection is established. It's kind of like probably some conversations that you've had in your life. But the two different protocols that allow us connectivity when we do this. TCP and UDP both have port numbers. And the ports are associated with applications. And the applications here are things like web servers, port 80, FTP, File Transfer Protocol 21, DNS, Domain Name Server, port 53, DHCP, Dynamic Host Configuration Protocol, to give us IP addresses, 66 and 67, I think. So each of the conversations that we have when we establish these, we're really, let's say we're talking about a subject that we're going to talk about. And the subject is going to be the port number. Subject is the port number. So I'll establish a connection to have a web server combination, or to find an IP address, DNS. We'll look at those in a little bit. But how are we going to connect these things? Connection-oriented, connectionless. TCP and UDP are the protocols that do that. So TCP transmission verifies that the data delivery is successful. Internet protocol ensures that the data packets can be tagged with information needed so as to be sent to specific networks. IP, and that's a whole lot of words to say. This is the address. This is the IP address. This is the network address. It's a non-proprietary routable protocol. It's a routable protocol. There are two types of protocols, routing and routable. Routing protocols are the language that routers use to talk to each other. Routable protocols are the ones that we use to find stuff. IPv4 addresses, we're going to have several different types, 3 different types that we're going to talk about. One's called a unicast address. A unicast address goes to an individual IP address. Communicate with one computer, one node, one printer, one thing at a time, are sent to a particular address. Addressings predominantly used in LANs and on the internet. So a unicast, we're going to a single device, Uni1. Broadcast address, and when I showed you that ARP, we had some that were 255s. 255s, and we'll talk a little bit more about the addressing here in a few minutes. 255s are going to tell us that it's broadcast, and a broadcast goes to all of the devices on our network, or at least on this side of the router. So broadcast used to communicate information from one node to all the nodes on the network, and that's probably about as far as we need to go with that one. A multicast is an address that goes to specific nodes, not all of them, but some of them. How that makes sense. You subscribe to that. It's kind of like a streaming broadcast might be a multicast address, so that only the devices that were subscribed to it would get that information. So we have unicast, multicast, and broadcasts that are used in IP addresses. The IP address itself has 2 parts. A network part, and I have a whole bunch of slides here on how we make up an IP address, because I think a little bit of IP addressing is part of this, not to a great degree. You have to maybe configure some IP addresses, but we have a network part and a host part. The network part is the network address, the address that we're on. It's like the apartment building would be the network address, and I think what a lot of slides or books talk about is the network part is if you're going to a house address, the network part would be the street. The host address would then be the apartment number or the house number that we were going to. A host part and the network part. The network part is defined by a subnet mask. We're going to have two parts of the address, and we're going to have a whole bunch of slides that go through this, and hopefully it'll make some sense when we get through with it. But we have a network address. We have the network portion of it. If we have, let's say we have an address 192.168.1.7. The subnet mask would be written something like 255.255.255.0. Everything with the 255 is a network portion. Everything with a 0 is going to be the host address. So the network address for this would be 192.168.1.0. The broadcast address, the one that went to everybody, would be 192.168.1.255. And when we look at the conversion, 255 is going to be the last address in here. The length of the subnet mask determines the network number. 10.2.3.4 subnet mask of 255, the network number is 10. The 192, the one that I just did with all these, is going to be 192.168.3.0. So it's going to be, the subnet mask tells us how much of the address is network. And once it tells us how much is network, everything else is going to be host portion of the address. IP address, the network segment. This is and the next slide will show how we get this binary to decimal conversion. Yeah, you got binary to decimal calculator on Windows. The only problem is when you take these tests, they don't let you use that calculator. On this one, we have the network segment and the node segment, it says, but we don't see what the subnet mask is here. It should be 255.255.255.0. So the network portion of this one would be 208.123.45.0. The .zeros are the network addresses. The broadcast address would be 208.123.45.255. So we have an IPv4 address written in decimal called a dotted quad, or octets, 8 bits, called octets. So each of these addresses is going to have 8 bits, 8 binary bits in it. The way we get there is in binary, as in all numbering systems, we have placeholders. So the value, the weight here, as we go from right to left, from the least significant to the most significant digit, we can go to powers of 2, or we can multiply by 2. We start out with 2 to the 0. Any number to the 0 power is 1. Any number to the first power, 2 to the 1, any number to the 1th is going to be the number itself. Or we can start out with saying, okay, I know the first one's 1, and then multiply it by 2 since it's binary. The advantage of binary is you only got to be able to multiply by 2. So we got 1, 2, 4, 8, 16, 32, 64, 128. That's the value of each of those placeholders. So if we had a binary number there, 110111010, down there in example 1, it would be 1 times 128 plus 1 times 64 plus 0 times 32 plus 1 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1, which is going to give us the 218. So the binary to decimal to binary, binary to decimal conversion can be done in a chart like this. The subnet mask 255 we talked about, 139.87.140.76, 255.255.0.0. It says removes the node portion of the IP address, zeros. What the computer does in this thing, and I'm just going to make up some ones and zeros. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. The subnet mask, this is going to be the host portion. Subnet mask 255. 255 is going to be all ones. You can add those up. You can trust me on that. So 255.255. when we do that, regardless that we end this process in Boolean algebra, whatever the numbers are here, when we end it with 1, it's going to be that number. So we end it, it'll be 1, 0. And this is a whole lot of to tell. This is the way the computer works to tell it. It's going to be the same number again. The subnet mask, when we have all zeros, when we end anything with a 0, we're going to get a 0. So what it does, and what this is saying, removes the node portion of the IP address. It's going to put zeros in the network portion. So what we're doing here is taking the IP address, ending it with the subnet mask. When we end with the 1s, we're going to get the 137.87. When we end it with zeros, we're going to get zeros. So 0.0, that's going to be the network ID or the network address for this particular IP address. This is just another one, and this slide, unfortunately, this came from a CCNA. This has got some mistakes on it because the subnet mask cannot, and I'll leave it like this, this can't be a subnet mask. Subnet mask, we go 1s until we start with zeros. When we start with zeros, it's got to be all zeros. So it's all 1s until it's all zeros when you look at the subnet mask. If you see something like that, that's not a legal subnet mask. But on this one, when we do this, it goes crazy. Yeah, I don't know what they did with this. The network portion of this one would be 110.1100.000000100 and the node portion, when we end it with the subnet mask, all zeros here will be all zeros. This is correct, and then we could convert this number back to decimal, and it would make a whole lot more sense to us. The computer uses binary. They actually tried to use decimal in the early days, but the voltages were unstable. So if is it an 8 or is it a 9 based on the voltage level? Binary is easy because it's either on or it's off, and they convert them that way. We have some default subnet masks. We have some class is of network addresses, and they're going to be A, B, C, D, and there is an E that is experimental. A, B's, and C's are the only ones that we use. D's are going to be multicast, which we can't do anything with multicast addresses. So the classes are going to be A, B's, and C's. The network's divided from the host on the octet boundaries, and the subnet mask will always have all 1s or all zeros in the octet for class full network addresses. The subnet mask, the default 255s or zeros. Class D's and E's, which exist but we don't use them, don't have subnet masks. We can only use A's, B's, and C's. So for the A, the subnet mask is 255.0.0.0. This thing over here, and one of the objectives said CIDR. CIDR, classless internet domain routing. CIDR is what this is over here, /8. What this means is that there are 8 1s in the subnet mask. 255.255.0.0. Class B are /16. 16 1s in the subnet mask. 8 and 8 is going to be 16, obviously, because each of these are octets. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 for the zeros for everything else. So the /, the CIDR, is just simply how many 1s are in the subnet mask. Class C, 255.255.255, 8, 16, 24 /24 for the CIDR representation of the subnet mask. IPv6, when we get there, you'll appreciate CIDR if you don't have to write the subnet mask. I think we've talked about that. The 1s in the mask start at bit 32 to the left of the mask. The zeros start at bit 1 to the right of the mask. The 1s in the mask must be contiguous with no zeros interspersed. Each subnet must have its own unique network ID. All devices on the subnet must share that network ID. So they're on the same network, they can talk to each other. Otherwise, they have to go through a router to get from one network to the other. Convert the IP addresses, use the AND operation. That was one of my bad drawings, was the AND operation. Gateways converts data between incompatible systems. Gateways would be if you were connecting to a mainframe using a desktop, for instance, you would have a gateway. And we got the gateway here 2 times. And one of the things that gets really confusing, particularly early on about networking, is when we use the same word to mean 2, 3, 4, 5 different things. So we have gateway and default gateway. So a gateway translates data between different operating systems. Can be a hardware, software, or both. The default gateway is the address of the router that gets you off of your network. If you don't have a default gateway in your IP addressing, you're not going anywhere except on your own network. You have to get to the default gateway. The default gateway is the router that's going to take you to the internet or to the other network that you need to go to. It's not required, but limited communication is not present. You'll be limited to the network that you're on. Address classes again, and I got another slide down here basically going to say the same thing. Class A, the subnet mask, 16,777,000 nodes per network. Class B, 65,534 nodes. There are actually 65,536 addresses, but we can't use the address that's all zeros for the host part because that's the network address, and we can't use the one that's all ones for the network address, 255s, because that's going to be the broadcast address. Everything else can be assigned to a node or to a device. And then the Class C's 254 nodes, 256 addresses. We have to take out the network address, and the broadcast address can't be used to be assigned to devices. Maybe a little bit different image here, the Class A's, B's, and C's, and how many addresses are on each of them. And then we got the private address range. IPv4, we actually are out of addresses. The last addresses have been assigned, were assigned probably about 1.5 years ago. But what we have that we can use inside of our private networks, and if you look at the IP config on the network that you're on with the command prompt or at home you're probably on a 192.168, and I think if you're at LeaderQuest, they use the 10 networks, the private networks we can use without having to pay for them. So we can use them. The 10 network for the Class A, the 172.16 to 172.31 for the Class Bs, and then the entire 192.168 range. And that's the one that I write for my examples all the time because I've used them so much that's just the one that comes to me. And we're going to talk about a people automatic private IP addressing in a little bit. They start with 169s, and that's kind of a Microsoft thing. If you can't get an IP address automatically, it gives itself one, and it gives it that address. CIDR, we talked about a little bit, 255.255, 192.168.12. CIDR combines the address with a number. They kind of messed us up here. I think that for this one, you don't have to worry about anything other than class full addresses. If anybody has had to deal with subnetted addresses, which is what this one is here, let me know. But 192.168.12 with a 255.255 would be /24. The 255.255.254 is actually going to be 23.1, so it'll be /23. Each of these, the 192.168 with the 255.255.255 would be /24 for the CIDR notation. IPv6 addresses, big addresses, 128 bits. There are, 340 undecillion, 348 undecillion. And that's a huge number. I saw something today that said that if, let's see, was it 6.8.6 billion people could have like 5 quadrillion addresses each. So we may or may not ever, not in my lifetime, we're going to run out of them, but you may or may not ever run out of them. IPv6 addresses are written in hexadecimal format, like the example there, and instead of writing out an entire subnet mask in hexadecimal, we use the CIDR notation /64. Says that the first 64 bits of this address is going to be the network portion of it. So the IPv6 increases the available pool of IP addresses. New efficiency features. It is more efficient, not compatible with IPv4. It says its deployment is limited. It's getting more and more and more deployed in the US. My ISP actually does provide me with an IPv6 address. And if an IPv6 destination address is available, it prefers IPv6 over IPv4. It's more secure, it's faster, and it is a more efficient protocol. The address length, IPv4 32 bits, IPv6 128 bits. IPsec, IP security, is optional in IPv4. It's required in IPv6. We can add security to IPv4 addresses. IPv6 has security by default. And the deployment here, widespread and limited. It is limited. It's becoming more and more available. The rest of the world's been using IPv6 for a long time. The issue that we got into was some hardware had to be updated to support IPv6. Windows has supported IPv6 since Vista. So it's been there. It's just not been activated on all of them. Windows 10, it's there by default. And if you can get an IPv6 address, it'll take an IPv6 address. Addressing schemes. Private IP addresses we looked at, the 10, the 172.16 to 172.31, 255, 255, and then the 192.168 entire network or IP addresses organizations use for the nodes requiring IP connectivity within the enterprise network, and we'll talk about how we get on the internet with those addresses a little bit later when we talk about a process called NAT, Network Address Translation. The public IP addresses and those private IP addresses are not routable on the internet. They have to stay inside the private network. In IPv6, these are called link local addresses. They're there, link local private addresses. Public addresses are addresses that connect computers to the internet, and they're assigned by an organization called ICANN. So they assign the addresses, they assign the routable addresses, the ones that can get you from one point to the other over the internet. Windows computers, an IP address with a 169.254/16 block that is automatically assigned when there's no DHCP server. We're going to talk about DHCP and look at a DHCP server a little later in this section. But DHCP is a protocol known as Dynamic Host Configuration Protocol. It's the beast that automatically gives you an IP address. So what that's saying is that if I didn't automatically get an IP address and I tried to get an IP address, I didn't get one, and I'll give myself one. And it starts with 169.254. These are not routable. You can only communicate with devices that are on your own network. And then we have a loopback address, a special address. 127.0.0.1 is the actual address. The network address is 127.0.0.8, a Class A network address. So we use 16 million addresses, possible addresses, in order to use one. It's reserved for loopback. Send out the device and write it back to the source without any processing. When you start troubleshooting, when you start pinging, and we'll talk about the ping, in a little bit. Most of the recommended troubleshooting is to ping the loopback address first to be sure that the NIC is actually working. The only easy address in IPv6 is the loopback address, and it is : 1. All the rest of them are much longer. They can be simplified, and I don't know that it's part of this, but if I can, I'll go over that with you. Two different ways that we can get IP addresses: static and dynamic. Dynamic is the DHCP obtain the IP address automatically. Static is when we type in the IP address. DHCP, Dynamic Host Configuration Protocol, and I wanted to show you a DHCP server. I've got to start this Windows server here, if it'll start for me. Lots of things running on my machine here. So it is actually restoring the virtual machine because it was in a save state, was paused, doesn't have to reload the operating system. This is the one that we did the raid on last night. So when I look at it at administrative tools, and I have DHCP, what it allows me to do in IPv4, I create a thing called a scope, which has a range of addresses that this device is going to give out. It has some scope options, like the router is going to be the default gateway. The DNS server is going to be the server that translates the names www.yahoo.com into an IP address so that it can actually go out onto the internet. So when we have these things, and then it keeps track, none of them have been given out, but it keeps track of its leases. When it runs out of leases, it quits giving them. Nobody can get a new IP address. So you have to be careful with these things. But it gives out the IP address and other information that's used by us. It's a broadcast protocol, and this is just showing we have the DHCP server here. We send a request out for an address, and it's going to give us one. It is a four-step process: discover, offer, request, and acknowledge, and called DORA. That's another thing that I think that in Network Plus will be something you need to know, but not necessarily for A+. So it sends us the IP address assignments when we ask for them, and by default all Windows machines are dynamic or configured for dynamic addresses. So when they start up, they're going to ask for a DHCP address. In your home router, it's probably going to be the device that is the DHCP server. So we have here DHCP settings, DHCP enabled, and this is in the network connection details. The address that we got, the subnet mask, the DHCP leases the address to us for a specified period of time. In this case, it tells us the lease was obtained on July the 27th and it's going to expire on July the 28th. Pretty short lease. You may or may not want to make it that short. It also gives us the IP default gateway we saw on the server, which is the address of the router to get out of it, the DHCP server that gave us the address, and then the DNS server. DNS server is the one that's going to translate our English words into IP addresses. DNS, now I've got a DNS server on this guy too, is going to translate our names into IP addresses. This one probably doesn't have a whole lot of current ones in it, but if we look at the .com here, google.com, we have a bunch of name servers. Let's see if I can This one doesn't have any actual real, because they time out. Let's see if we can get one. Okay, so it didn't. See, this one did an IPv6. We can tell it that we want to do IPv4, I think, to get, because this is an IPv6 look here. What we have to do then is refresh it, and we'll see if Yahoo came up here. Yeah, here is my www. Yahoo.com. When I look in it, it's going to tell me what the address is. And this has got some in it. Oh, this tells me what the alias is. I should look for this guy instead of www.yahoo.com. But we can look in here, the name server, NS3, host A records are ones that are for individual machines, and then it relates a name, ns3.yahoo.com, with an IP address. This lists both IPv6 and IPv4 addresses. And so when something wants to look up an address that it doesn't have, the first thing it's going to do is to go to its local DNS server. If it's there, if it's in the cache, which we were looking at, it's just simply going to give you that IP address. Otherwise, the DNS server goes to the root, says, I want the address for www.yahoo.com. The root server says, I don't know what that is, but I know where the top-level domain .com server is. So it gives us the address of the .com server. Come back down. We then go to the .com server and say, I want the address of www.yahoo.com. I don't know, but I'll tell you where Yahoo's server is. So it gives us that address. We go to the Yahoo name server and say, I want the address of www.yahoo.com. It tells us what the address is of the www server. www represents a computer somewhere, a server somewhere in the world. This is what that one is. While I retrieve the information for you, it goes to the root, to the COM, and then to the DNS server of that particular organization. Organizations maintain their own DNS server to find their resources. ISPs, we have internet connectivity through our ISP, our internet service provider, when we do those things. The connection types, this table I think is in the book. We have cable, DSL, dial-up. Hopefully you don't have that anymore. Fiber, that's what FiOS is about. Satellite, if that's the only thing you can get. I had a friend who had that one time. He said it was absolutely miserable because of the delay. ISDN, not so much anymore. Cellular, if you set up your cell phone maybe as a Wi-Fi hotspot, would be a cellular connection. Line of sight, wireless connections, and these are kind of, or they're focused dishes that do that. I mean, a friend, same guy who had the cellular, he lives out in the country, now has a wireless wide area network. He has to be able to see a particular mountaintop in order to get the signal, and they use dish antennas in order to focus it so he can get a signal. Tree grows up in the way, you're going to have a problem. You have to be careful about objects. You have to have unobstructed view of these things. TCP, UDP, we've talked a little bit about that. I told you why it's connection oriented, the three-way handshake. Breaks data up into datagrams, reassembling it, then sending them. If there's too much, it sends them in. The way that I've always tried to think of this initially is maybe you're going on a roller coaster. Not that we're going to have a tumultuous ride, but we're going from one place to the other. You have people in line. That's going to be your data that's going to get into the cars. So a group of people get into the cars. That's going to be a datagram. People in the next car, that's going to be a datagram. So we break these things up into more reasonable chunks in order to send them. And we number them. It'd be car 1, car 2, car 3, data packet 1, 2, 3, but they are much bigger numbers. So that when we get to the other end, we'll be sure that all the cars got there, which would be unlikely with the roller coaster, but you may lose some data as TCP goes through there. So it's going to be reliable. It's going to acknowledge receipt of the data when it gets from point A to point B. UDP is connectionless. There's no startup, no connection when it starts up, no flow control, no error control, no recovery. It is less complex, faster service. It's not like you lose a lot of data when you have these things. UDP is something that would probably use for streaming, whereas TCP would be used for transfer of an important document, for instance. Where would you use which one? When you need to be sure that everything got there is TCP. UDP, streaming video, streaming devices, telephone calls. Our analog ears and eyes will fix a lot of errors if they're really, really small errors, and they're going to be really, really small packets with these things. Before we talk about ports here for a few minutes, let's go ahead and take a break. What this weird thing is on your screen is a Wireshark, which is a free network sniffer if you want to see what kind of traffic's on your network. Just to show you that the SYN, the SYNAC, and the ACK, it's TCP. We have the source IP address, the destination IP address, the source port, and the destination port. Each end has to be a socket. It has to have a port number and an IP address, an IP address and a port number. The destination here, 443, is HTTPS, and then we come back, the 51687 would be the machine that I was using to get there. Going to 443, we have a synchronized, and there are some sequence numbers over here. And then we have the SYNAC and then the ACK. Once that happens, we have the conversation started. We can then start sending information, and after that we should just get acknowledgments of the receipt of the data. If you look down in the frame information, let me try to go back. I really do want you to see this 10 minutes, and you couldn't yell at me, I know. You tried. So what we started out with, really don't want to see very often, but we have a three-way handshake, the SYN, the SYNAC, and the ACK, and we have port numbers that are associated with these things. I know why that is. That's a DHCP. That's not the one that I wanted. I wanted the HTTP. So when we go down here, we have a lot of different things. This is Wireshark, which is an open source network sniffer. So we have here the three-way handshake, which actually goes somewhere. We're going to 443, which is going to be a secure HTTP connection, and then it's going to answer me back with the SYNAC. And after we start having the conversation, the port numbers here are going to just start acknowledging receipt of the data. When you look down in here, we have the MAC addresses, the IP addresses, and the TCP, the port numbers, the source port and the destination ports for the devices themselves. So these are a list of ports. These are the common ports that I've read, at least from the Professor Messer study guide, and these came from it. These are the ports that you need to be aware of. FTP, and this one is good. You can get it in the guide, and it doesn't probably do a whole lot of good for me to read them to you, but the protocol, the port number, the name of it, and then what that protocol actually does. Protocols, a little bit of some LDAP, lightweight directory access protocol, is in fact a directory. It defines how a client can access information, perform operations, and share data directory. Active Directory in Windows is an LDAP protocol, Lightweight Directory Access Protocol. SNMP, Simple Network Management Protocol, collects information about devices. You may have seen somebody watching how much bandwidth is being used on a switch. That's being sent to the workstation using the SNMP protocol. There are a number. If you want to play with one, PRTG, you can look up with on Google, will give you a freeware version of their SNMP application protocol. What we have here is the agent here that sends the information to the management, the program that's running on a workstation that will give us a visual display of what's going on the devices. One of the things probably you may have seen in management, or maybe not, but you may get a message from a printer if you're assigned to it it's low on paper. It's out of paper, or that the print cartridge is empty. Those sorts of things. SMB, Server Management Block, it's a file and print protocol that Microsoft uses to share information. Print and file sharing are established or done through the SMB protocol. CIFS, Common Internet File System, is file sharing across operating systems, and it's going to be related to SMB. SSH, Secure Shell, gives us an encrypted, it's a Linux-based protocol, an encrypted connection from one device to the other. Where this one is predominantly, as well as Telnet, are predominantly going to be used, or where I've used it the most, is to connect to a router or a switch to configure them remotely. It's going to be an encrypted, it says password encrypted, it's going to be an encrypted connection when we do these things. You have to log in, you have to do the configurations, obviously, in order to get it to generate the keys to do these things. AFP, Apple File Protocol, still used by some Mac computers. SMB2 is used to communicate between Windows and Microsoft. So they can communicate, not as bad as they used to be about not being able to talk to each other, but SMB2 is used for communication between the two major operating systems. The protocols that we've talked about a little bit before, DHCP, DNS, we looked at. LDAP, we talked about. SNMP, and this is another one that comes from the Professor Messer. SMB, SSH, encrypted remote console login, the Apple File Protocol, and then SLP, Service Location Protocol, finds services in the Mac OS services by name that are going on. NetWare used to do that also. Now we'll get to hopefully the easy portion. This is, I think, where I was when you guys finally got my attention. A cable tester, media tester, checks to be sure, if we make cable, checks to be sure that the cable, the simple ones, that it has end-to-end connectivity. If we want to check the transmission quality, we've got to get something that's a little more expensive than the simple tester. The simple tester, yeah, we made it right. We've got the wires in the right place. We got them crimped, and yes, we have connectivity. Cable strippers, a wire stripper, sometimes part of a wire crimper, used to strip wires of their protective coating. On the RJ45s, we will strip off the outer covering, but on the wires themselves, the twisted wires themselves, we just untwist them and put them into the connector, and use the crimper in order to crimp it, and it will drive the little nails into the, my best description of it, into the wire so that it has connectivity. Attaches the media connectors to the ends of the cables. You can make your own cable with it. different types of crimpers for different types of connectors. They're not outrageously expensive. You can get them at a lot of hardware stores. I think that Home Depot and Lowe's both have them if you want to make your own wire. Wire stripper is often part of the crimper, and it may be, and again, you only strip the outer casing on the RJ45, the twisted pair. Multimeters, we talked about those when we talked about power supplies. Measures voltage, current, and resistance, and we talked about the power supplies to see if we had the correct voltage for them. A tone generator, this is one that I think they may ask you. What a tone generator does is it generates a tone, and it sends a tone down the wire. And then you use the detector here in order to find where the wire is. We moved into a building one time and it had wire all over the place. Some of it we could reuse and some of it we couldn't. But in order to find out where the wire actually went, we needed a tone generator to find out from end to end where it went from when it point to point, where it went from to. And most commonly used in telephone systems to trace wire pairs. It can be used in network to find out where one is. Loopback plugs. I think we've talked about this before. What it does is on the RJ45, it loops back the transmit to the receive, crosses over these two so that we can see if the signal's going out and coming back in to the RJ45 port. Punch down tool is used in the wiring closet. This is used in the patch panel to push the wire into the patch panel and cut it at the same time. You see the little scissor symbol here. You punch down the wire into the receptors on the patch panel, and then at the same time it's going to cut the wire off so that we will then be able to have those. Makes connecting wires to the patch panel easier. If you buy an RJ45 a receptor, the last one I bought had a little bitty punch down tool, so they told you what colors to put where, and then you punched it into the outlet. A Wi-Fi analyzer detects problems in wireless LANs, can detect the wireless devices, points of interference, overall health of the wireless LAN. These are a couple of them. This says it's a Wi-Fi analyzer here. This is actually one called Insider, INSSIDER, which I think you can get for free. It gives you some information. The devices here, this one's a little bit hard to see, but it tells you the network, and then it shows you the signal down here, how wide the signal is, what channel it's on, and this one uses the 2.4 gig as well as the 5 gig range in order to do that. So you can look at what's going on. When you look at your wireless, there are only 3 real 2.4 gigahertz channels, and those are 1, 6, and 11. Everything else, and we'll see that tomorrow night, everything else is going to have some overlap. An actual real analyzer, spectrum analyzer on the Wi-Fi is what this thing would look like. It's going to see noise. The red down here is noise, and then we get into green, blue, that you can see signal interferences on these things. What's going to interfere in anything on that frequency? Microwaves are a big problem with them. The networking utilities, I said we would look at, let's just talk about them. Ping is IP config and IF config. IP config for Windows, IF config for Linux. Displays the configurations. Ping checks the connectivity. Is the device alive at the other end? Tracer T and trace route. These are all different ones. They're for Windows as well as for Linux. Let's see if we can do. What trace route does is checks the entire route, checks the routers themselves when we go from one to the other. NS lookup is going to check our DNS server. NetStat shows the status of the active network connections. This is one that you may want to run on your own machine to see if anything odd is connected to your machine. It will show you all of the connections. Some of them are going to be passive, waiting for connections. Some of them are going to be active connections. Net bunch of stuff is Microsoft management. Local area connection or wireless network connection, that the devices are connected and send and receive data. And then network troubleshooters, wizard interfaces to work through possible causes and resolutions. I had hoped to finish a little earlier, but